Tonight we're going to talk about something your brain does without telling you. Every night it builds a world from scratch, places, people, whole conversations, and you believe every bit of it until you wake up. That's not the unsettling part. The unsettling part is what happens when physicists start asking whether waking up actually changes anything. There's an old equation carved on a tombstone in Vienna, and if you follow it far enough, it asks a question you can't quite answer. How do you know any of this, the room, the dark, the memories you're carrying right now, is real? It's a gentle kind of question, the kind that's best explored lying down. There's something worth noticing about tonight. Right now, wherever you are, your brain is doing something it does every single day without asking permission. It's deciding what counts as real. It takes in light and pressure and sound, runs all of it through a web of electrochemical signals, and hands you a finished product, the world, a seamless, convincing, utterly persuasive version of what's out there. And for the most part, you never think twice about it. But every night, that same brain does something else, something a little unsettling if you sit with it long enough. When you fall into REM sleep, a specific part of your brain, the dorsolateral prefrontal cortex, the region most associated with logical reasoning and self-monitoring, goes largely offline. It just steps back. Meanwhile, deeper structures light up, the amygdala, which processes emotion, the hippocampus, where memories are formed and retrieved, the visual cortex, painting images behind your closed eyelids, and what happens next is, by any honest measure, extraordinary. Your brain builds an entire world from nothing. You walk through rooms that don't exist. You talk to people, sometimes people you haven't seen in years, sometimes people you've never met at all, and you believe every word of the conversation. You feel things, relief, dread, a strange tenderness for someone whose face you won't remember by morning. The default mode network, that sprawling web of brain regions most active when you're not focused on any external task, takes fragments of memory, a hallway from your childhood, a feeling you had last Tuesday, the face of a stranger on a bus, and stitches them into something that feels, in the moment, like a coherent life. A narrative, a story with a beginning and a middle and what seems like it must be going somewhere. And the whole time you don't question it, not once. You accept the dream as completely, unambiguously real. Your critical faculties, the ones that would normally say, wait, this doesn't make sense, they're asleep too. So the experience just washes over you, and you live inside it without a shred of doubt. That's the part that should give you pause, not that dreams are strange, everyone knows dreams are strange, but that you are, every single night, a conscious being whose entire reality is fabricated from internal signals, and you cannot tell the difference. Your brain is already proving, on a nightly basis, that it doesn't need an external world to give you a convincing one. Which brings us to a thought experiment that's been troubling physicists and philosophers for over a century now. And it starts, oddly enough, not with neuroscience or dreams, but with heat. In the late 19th century, the Austrian physicist Ludwig Boltzmann was working on the second law of thermodynamics, the law that says entropy, the measure of disorder in a system, tends to increase over time. Things fall apart. Hot coffee cools, ordered arrangements dissolve into chaos. That's the general direction the universe is heading, and it's one of the most fundamental truths in all of physics. But Boltzmann noticed something uncomfortable. If the universe tends toward maximum disorder, toward a kind of lukewarm, featureless equilibrium, then why does our corner of it look so remarkably ordered? Why are there stars and planets and living things and brains capable of asking this question in the first place? And here's where the story takes a turn that Boltzmann himself might not have fully anticipated. The idea that our universe might be a random fluctuation, a brief pocket of order bobbing up from an infinite sea of chaos, didn't actually originate with Boltzmann. He credited it to his assistant, a man named Ignaz Schewitz. In an 1896 paper, Boltzmann presented what's now called the fluctuation hypothesis almost as a passing thought, an aside attributing the core insight to Schewitz. That if you have a universe sitting in eternal thermal equilibrium, just an endless expanse of maximum entropy with nothing happening, then given enough time, and we're talking about timescales so vast they make the age of our universe look like a single heartbeat, that featureless void would, purely by random chance, fluctuate into pockets of order. Brief, improbable arrangements of matter and energy. Arrangements like the one we happen to be sitting inside right now. It's a strange kind of origin story, not a creation myth with purpose or design, but a statistical accident, a cosmic lottery ticket that nobody bought. And the troubling part, the part that kept later physicists up at night, which feels appropriate for where we are right now, is that the math doesn't stop where you'd want it to. Because if random fluctuations can produce an entire observable universe, they can also produce something much smaller, something much more likely, statistically speaking. A single brain. A disembodied mind flickering into existence for just a moment, complete with a full set of memories. Memories of a childhood, memories of a Tuesday, memories of reading something just like this, late at night, feeling a little drowsy, thinking about what's real. That's the Boltzmann brain hypothesis, and it's not a thought experiment dreamed up by science fiction writers. It falls directly out of the same thermodynamic equations that explain why your coffee gets cold. The unsettling implication is this: it is overwhelmingly more probable, given infinite time and the laws of entropy, for a single conscious mind to fluctuate into existence with fabricated memories of an entire life, than it is for an entire ordered universe to fluctuate into existence to actually give that mind a real life to remember. 24 centuries before any of this physics existed, a Chinese philosopher named Zhuangzi was already sitting with essentially the same puzzle. In a text from the 4th century BCA, he wrote about falling asleep and dreaming he was a butterfly, fluttering around, perfectly content, with no awareness of being Zhuangzi at all. And then he woke up, and he was Zhuangzi again, solid and certain. But then came the question, the one he left hanging in the air like smoke. Now I do not know whether I was then a man dreaming I was a butterfly, or whether I am now a butterfly dreaming I am a man. What makes Zhuangzi's version so quietly devastating is what he doesn't do with it. He doesn't try to solve it. He doesn't reach for proof that he's really Zhuangzi or construct an argument for the primacy of waking life. Unlike Descartes, who would come along 2,000 years later and use radical doubt as a kind of philosophical tool, doubting everything in order to find the one thing he couldn't doubt and building certainty back up from there, Zhuangzi just lets the question sit. The point, if there is one, is to dissolve the assumption that the distinction between dreaming and waking is the kind of thing that can be settled, or that it even needs to be. And maybe that's the strangest thing about tonight. Your brain will, in a few hours or maybe sooner, shut down the part of you that knows what's real and spin up a world made entirely of memory and invention. You'll live in it, you'll believe it, and when you wake up you'll call this the real one, not because you have proof, but because this is the one where you happen to be awake. Or at least the one where you think you are. There's a man buried in Vienna whose tombstone doesn't say a word, no name chiseled in grand letters, no dates marking the bookends of a life, just an equation. S equals K log W. It sits there in the stone like a quiet argument, one that outlasted every debate he ever had, every room he ever stormed out of, every sleepless night spent wondering if anyone would ever believe him. Ludwig Boltzmann spent most of his adult life fighting for something that sounds, to us now, almost embarrassingly obvious, that atoms are real, that the stuff of the world is made of tiny, countable things bumping into each other. But in the late 1800s, this was not a settled question. It was a war, and Boltzmann was on the losing side for most of it. His opponents were serious people. Ernst Mach, yes, the speed of sound Mach, and Wilhelm Ostwald led what was called the energeticist school, which sounds like a philosophy department but was really a movement to strip physics down to pure energy and observable quantities. They didn't just disagree with Boltzmann, they thought his atoms were a fantasy, a convenient fiction. Mach once said that he didn't believe in atoms the same way he didn't believe in elves. And Boltzmann kept showing up. He argued, he published, he lectured. At the 1895 meeting in Lübeck, he made the case so forcefully, so thoroughly, that he essentially won the room. The atomic view carried the day, but winning an argument and winning the peace are different things. The toll was already deep. Boltzmann's mind, brilliant, restless, capable of holding entire statistical universes in its grip, was also fragile in ways he couldn't always control. What modern psychiatrists would probably call bipolar disorder shaped his inner life as much as physics shaped his public one. There were periods of manic intellectual energy, weeks where the ideas came faster than he could write them down, where he could see connections between thermodynamics and probability that no one else had even imagined. And then there were the crashes, the long silences, the weight of it. Decades of being told that your life's work is wrong, not just mistaken, but meaningless, will do something to a person. Even a person who knows, somewhere underneath the exhaustion, that they're right. It's hard to talk about this part without feeling the heaviness of it, because the story doesn't resolve the way you'd want. On September 5, 1906, Boltzmann was in Duino, a small town near Trieste on the Adriatic coast. He was there with his wife and daughter, a vacation, and that's where he died by his own hand. The details are sparse and private, and maybe they should stay that way. What matters for the story, what makes it ache in a particular kind of way, is the timing. Because just months later, the proof arrived. Einstein's 1905 paper on Brownian motion, and Jean Perrin's meticulous experiments that followed, gave the world what Boltzmann had been begging it to accept for decades: direct, measurable evidence that atoms were real. That the microscopic world he had built his entire statistical framework around was not a useful metaphor or a mathematical trick. It was the truth. The little particles were there, jostling pollen grains in water, exactly the way his equations predicted they would. He missed it by months, maybe less. The vindication he had earned over a lifetime of work arrived to an empty chair. And so the tombstone, S equals K log W, the equation that connects entropy, the disorder of a system, the direction that time seems to prefer, to the sheer number of ways the tiny, invisible pieces of that system can be arranged. It's elegant in the way only physics can be elegant, which is to say it's not trying to be beautiful. It just is. A relationship so fundamental that once you see it, you can't unsee it. Every shuffled deck of cards, every cooling cup of tea, every drift toward disorder in the universe follows from what that equation describes. But here's the thing that makes the tombstone more than a monument. That equation, followed all the way out, taken to its logical, uncomfortable, slightly absurd extreme, is what gives us the Boltzmann brain. The same formula that counts the ways particles can arrange themselves also implies that, given enough time and enough randomness, any arrangement is possible. Including a brain. Including your brain, complete with all its memories, all its sense of having lived a life, all its conviction that it woke up this morning and made coffee and is now lying in bed listening to someone talk about physics. The math doesn't distinguish between a brain that formed through billions of years of stellar evolution and biological development, and one that flickered into existence from a random fluctuation in an empty void, fully loaded with false memories of a life it never lived. Boltzmann's grave marker is, if you tilt your head just right, the headstone for certainty itself. The equation carved in stone is the seed of a question that dissolves the ground beneath your feet. How do you know any of this is real? Not in a dramatic movie trailer way, in a quiet statistical way, in the way that the math, the math he gave everything for, says that the simplest explanation for your existence might not involve a universe at all. It's a strange kind of legacy. The man who fought to prove that the invisible building blocks of reality were real left behind an equation that, if you follow it far enough, asks whether reality itself is the thing that needs proving, and he's not here to answer. The equation just sits there in the stone, patient, waiting for someone to do the math. So someone did the math. In 1964, Richard Feynman stood in front of a lecture hall at Caltech and followed Boltzmann's logic all the way down. Not halfway, not to the point where it gets uncomfortable and you change the subject, all the way. And what he found at the bottom was essentially this: if you accept that the universe can fluctuate into pockets of order from disorder, which is what Boltzmann proposed and which the math supports, then the most likely fluctuation isn't a galaxy. It's not a solar system. It's not even a single planet with oceans and mountains and someone standing on it wondering how they got there. It's a brain. One brain floating in nothing, equipped with a complete set of memories of a life it never lived, sensory impressions of a world it has never touched, and just enough coherence to think, for one brief flicker, that everything is normal. Then it's gone, back to noise. Feynman didn't flinch from this. That was one of the things about Feynman. He had a kind of intellectual fearlessness that wasn't bravado. It was just genuine curiosity taken to its logical extreme. He looked at the fluctuation math and said, okay, if we're being honest, the cheapest way for entropy to produce everything you're currently experiencing isn't to build an entire universe. It's to build you, just the part of you that's doing the experiencing. Everything else, the room, the sky, the memory of breakfast, is unnecessary overhead. And for about 40 years, that idea just sort of sat there. Physicists knew about it. It came up in seminars, in late-night conversations at conferences, in the margins of papers about cosmology. But it didn't have a name yet, and unnamed things are easy to set aside. Then 2004 happened. Andreas Albrecht and Lorenzo Sorbo, two physicists working on cosmological models, published a paper in Physical Review D that finally gave the paradox a label. They called them Boltzmann brains, two words that sound almost playful, almost like a thought experiment you'd find in a philosophy textbook next to the trolley problem. But what Albrecht and Sorbo were actually doing was sounding an alarm. They'd been running the numbers on several of the leading cosmological models that were, at the time, considered our best descriptions of the universe, and they kept hitting the same wall. These models didn't just allow for spontaneous brains, they predicted more of them than real ones, vastly more, not a few statistical oddities around the edges, a flood. The ratio was staggering. For every genuinely evolved, biologically assembled brain that came into being through billions of years of stellar nucleosynthesis and planetary formation and natural selection, the math predicted an astronomically larger number of brains that just popped into existence from random thermal fluctuations. Momentary arrangements of particles that, purely by chance, happened to form something that could think, could remember, could look around and see a universe that wasn't there. Albrecht had actually been talking about this in seminars since 2002, and the response from the cosmology community was something close to collective unease. Because this wasn't a flaw you could patch, it wasn't a rounding error, it was a structural feature of the models themselves. If your theory of the universe predicts that almost all observers are hallucinating, then either your theory is wrong or you're one of the hallucinations. Neither option is particularly comforting at 2 in the morning. And then Lawrence Shulman made it worse. Shulman, a physicist who'd been thinking carefully about entropy and time, had articulated something back in 1997 that might be the most vertigo-inducing piece of the whole puzzle. He pointed out that it would take a smaller entropy fluctuation, less improbability, less cosmic effort, to simply rearrange the atoms already in your brain so that you falsely remember seeing a tree than it would take to actually fluctuate an entire tree into existence. Think about that for a second. The tree outside your window, if we're playing this game honestly, is overkill. A real tree with real bark and real roots drawing real water from real soil, that's an enormous amount of organized matter, an extravagant expenditure of low entropy. Your memory of that tree, by contrast, is just a pattern of neural connections. A few grams of tissue configured in a particular way. Nature, left to chance, is an economist. It takes the cheapest route. And the cheapest route to everything you think you've experienced isn't to build any of it. It's to build something that thinks it experienced it. This is the part where the Boltzmann brain problem stops feeling like physics and starts feeling like something else entirely. Because Schulman's observation means the argument isn't just about the origin of the universe or the deep future of thermodynamics. It's about right now, this moment, the specific collection of memories and sensations that constitute your experience of reading these words. The statistical argument says all of that is more likely to be a momentary fabrication than a faithful record of events that actually happened. And the thing is, you can't check. That's what makes it different from other skeptical puzzles. It's not like wondering whether you're dreaming, where you might eventually wake up and compare notes. A Boltzmann brain doesn't get a second opinion. It doesn't last long enough. So let's think about the numbers. There's a figure that gets thrown around in these discussions, and it's the kind of number that breaks your ability to think about numbers at all. By one standard calculation, a single Boltzmann brain, just one spontaneous flicker of conscious experience, would appear as a quantum fluctuation after roughly 10 to the power of 10 to the 50th years. That's not a typo or a rhetorical exaggeration. If you tried to write that number out in full, digit by digit, you would need more digits than there are particles in the observable universe. You literally cannot write it down. There isn't enough stuff in reality to represent it. And set against that the current age of the universe, the entire span of time since the Big Bang, every star that has ever burned, every galaxy that has ever formed, is 13.8 billion years. On the timescale we're talking about, that's nothing. It's not even a rounding error. It's essentially zero. The universe hasn't even started yet, in a sense. But here's the thing about eternity. It doesn't care about big numbers. If you have forever genuinely, mathematically forever, then even an event with a probability so small it would take more digits to describe than there are atoms in the cosmos. That event happens. It happens an infinite number of times. Eternity always wins. That's not a philosophical claim. That's just what infinity means. Given enough time, every possible configuration of matter and energy occurs, including, somewhere in the unfathomable depths of the far future, a brief arrangement of particles that experiences itself as a person sitting in a room, remembering a life it never lived. And the uncomfortable part is that current cosmological evidence suggests we're living in exactly the kind of universe where this isn't just possible but, in some sense, inevitable. The universe, as best we can tell, is what physicists call a de Sitter space. It has a positive cosmological constant. That's the dark energy you hear about, the mysterious force that's pushing everything apart at an accelerating rate. What that means, practically speaking, is that the universe will expand forever. It won't collapse back on itself. It won't cycle through some grand loop. It will just keep spreading out, getting emptier and colder, approaching thermal equilibrium, the heat death, the long silence at the end of everything. But the end of everything is misleading, because in a de Sitter space, things don't actually end. The universe doesn't switch off. It just becomes very, very quiet. And in that quietness at the cosmological horizon, the boundary beyond which light can never reach you because space itself is expanding too fast, there's something called Hawking radiation. The same phenomenon that causes black holes to slowly evaporate also applies to the cosmological horizon of a de Sitter universe. It's faint, impossibly faint, but it's there, and through a process called nucleation, that radiation can, given enough time, give rise to momentary structures, Boltzmann brains among them. So the mechanism is real, the physics is real. The timescale is absurd, but the timescale is also infinite, so absurdity becomes certainty. This is where the problem gets genuinely difficult, not just as a thought experiment, but as an actual crisis in theoretical physics. Because the Boltzmann brain problem, it turns out, collapses into something called the measure problem, and the measure problem is one of the deepest unsolved questions in cosmology. The issue is deceptively simple to state. How do you assign meaningful probabilities in an infinite universe? If space is infinite, or if time is infinite, or both, then everything that can happen does happen, and it happens an infinite number of times. So when you try to calculate the probability of being a normal observer, someone who evolved on a planet, formed memories through actual experience, exists in a universe with structure and history, versus being a Boltzmann brain, a momentary fluctuation that merely seems to have all those things, you're dividing infinity by infinity. And that doesn't give you an answer. It gives you whatever answer you want, depending on how you set up the calculation. Alan Guth, and this is worth pausing on, because Guth isn't some fringe figure. He's one of the architects of inflation theory, one of the people who built the modern understanding of how the universe began. Guth has acknowledged that this creates a genuinely disturbing possibility. If you can't solve the measure problem, if you can't find a principled way to count observers in an infinite cosmos, then the math suggests something deeply strange. A randomly chosen observer would be overwhelmingly likely to find themselves alone in an empty void, not surrounded by stars and galaxies and other people, not on a planet with a history stretching back billions of years, just floating, briefly conscious, full of false memories of a universe that doesn't exist around them. That's not what we experience, obviously. We experience structure, consistency, a universe that seems to follow laws and have a past, but Guth's point is that we can't currently explain, in a rigorous mathematical sense, why our experience should be typical rather than wildly atypical. The tools we have for making predictions in cosmology, the ones that work so beautifully for calculating the cosmic microwave background or the distribution of galaxies, those tools break down when you try to apply them to the question of which observers are most common. And that's an unsettling place to be, not because anyone seriously believes we're Boltzmann brains, most physicists don't, or at least they hope they don't, but because the inability to rule it out formally points to something missing in our understanding, some gap in the foundations. The Boltzmann brain problem isn't really about Boltzmann brains. It's about whether our best theories of the universe can account for the fact that we're here, in this particular way, having this particular kind of experience. It's late, and these are the kinds of thoughts that settle in when the day's noise has faded. The idea that somewhere in the deep mathematics of cosmology, there's a question mark hanging over the most basic fact of your existence, not whether you exist, but whether the context you exist in is real. Whether the memories that feel so solid, so textured, so yours, are anchored to anything at all. And so you sit with that, the question mark, the faint vertigo of it, and maybe you think, well, that's just philosophy. It's just a late-night thought experiment, the kind of thing you entertain for a moment before the weight of ordinary life pulls you back. But here's the thing that makes the Boltzmann brain different from most late-night thought experiments. It isn't just philosophy, it has teeth. Cosmologists, working physicists, people who build mathematical models of the universe for a living, actually use the Boltzmann brain as a kind of test. A litmus test, really. When someone proposes a new model of how the cosmos works, one of the questions that gets asked, sometimes almost reflexively, is, does this model predict more Boltzmann brains than real observers? And if the answer is yes, if the math says that given enough time and enough space, random fluctuations would eventually produce more lonely, momentary consciousnesses than the kind that evolved slowly on planets, then a lot of physicists will look at that model and say, something's wrong here. Not wrong in a hand-wavy, feels-bad way. Wrong in the way a prediction that contradicts observation is wrong, because if Boltzmann brains outnumber us, then we should probably be one, and we don't seem to be one. So the theory that predicts it probably needs fixing. It's a strange kind of scientific tool when you think about it. A 19th century thought experiment about entropy and randomness, something Ludwig Boltzmann himself might have considered an intellectual curiosity, has become a surprisingly sharp constraint on 21st century physics. It's like discovering that an old philosophical riddle, one you thought was just meant to make you feel uneasy at dinner parties, actually has the power to rule out entire theories of the universe. The Boltzmann brain isn't just asking you to feel uncertain. It's asking physics to be more careful. And that's part of what makes it sit differently than other skeptical puzzles. You've probably heard of Descartes' evil demon, the idea from 1641 that some all-powerful deceiver could be feeding you a completely fabricated reality. Every sight, every sound, every memory, all constructed by something you can't detect. It's a famous thought experiment, and it's genuinely unsettling the first time you encounter it. But here's the thing about the evil demon, there's no particular reason to think it's likely. Descartes wasn't claiming the demon was probable. He was using it as a tool, a way of asking what we can know with absolute certainty if we strip away every assumption. The demon is a pure philosophical hypothesis. Nothing in the laws of physics suggests it should exist or that it's more common than not. The Boltzmann brain, though, the Boltzmann brain is different. It's sometimes called the physics version of Descartes' demon, and the comparison is fair up to a point. Both ask you to consider that your experience might be fundamentally unmoored from reality. Both suggest that everything you remember, everything you believe about your past could be a kind of illusion. But the Boltzmann brain doesn't need an evil demon. It doesn't need any external agent at all. It just needs the universe to be very, very large and very, very old, and for the laws of thermodynamics to work the way we think they do. And in many mainstream cosmological models, not fringe ideas, not speculative philosophy, but models that serious physicists take seriously, the math says that the ratio of spontaneous brains to evolved ones isn't just large, it's infinite. That's worth sitting with for a moment. The math does the demon's work for free. No malice, no design, no intent, just probability and time and the blind shuffling of particles. The universe doesn't need to be out to get you. It just needs to be big enough and patient enough, and the Boltzmann brains emerge on their own, as inevitable as the occasional winning hand in a card game that never ends. And if that feels like a modern anxiety, something born from our particular moment of cosmological knowledge, well, it's worth knowing that the general shape of this worry is older than you might think. In 1921, the philosopher Bertrand Russell posed what he called the 5-minute hypothesis. The idea is simple, and once you hear it, it's hard to fully shake. Russell asked, what if the entire universe sprang into existence 5 minutes ago? Not the broad strokes, everything. Every fossil in every rock layer, every photon of light traveling from a distant star, positioned exactly where it would need to be to look like it had been traveling for billions of years. Every wrinkle in your grandmother's face, every memory in your head, all of it assembled in an instant, complete and coherent and utterly fabricated. Russell acknowledged, and this is important, that the hypothesis is logically irrefutable. You can't disprove it. Any evidence you offer against it, old photographs, carbon dating, the cosmic microwave background, is exactly the kind of evidence that would exist if the hypothesis were true. It's self-sealing in the way that the most unsettling ideas often are. He didn't mean it as a serious proposal. He originally framed it as a tool for thinking about what memory actually is, what it means to say you remember something, and whether the feeling of remembering is the same as having a real past. But reading Russell's 5-minute hypothesis today, it feels like something else. It feels like an uncanny philosophical ancestor of the Boltzmann brain. Both ask the same quiet, destabilizing question, not whether your experience is real in this moment, but whether it's connected to anything before this moment. Whether the thread of your life, the one that seems to stretch back through years of accumulated experience, is actually attached to anything, or whether it's just a loose end floating. The 5-minute hypothesis and the Boltzmann brain aren't identical, of course. Russell's version is a logical exercise. The Boltzmann brain is a physical prediction. But they rhyme. They share the same deep unease. And there's something almost poignant about the fact that a philosopher in 1921 was asking essentially the same question that cosmologists would formalize decades later, not because he had the math, but because the worry is so fundamental that it keeps finding new ways to surface. So maybe that's the thing to hold on to as the night settles in a little deeper. These aren't just ideas that clever people invented to make you feel small. They're ideas that keep arriving independently from different directions, from philosophy, from physics, from the quiet hours when you're alone with your own thoughts. The question of whether your memories are real, whether the past you carry is genuine or just an elaborate arrangement of matter that happens to feel like a past, it's not something you can fully answer. But it's also not something you can fully ignore. It just sits there, patient, like a question that knows it has all the time in the world. And there's a strange thing about that question, the one about whether your memories are real. It doesn't just sit there. It pulls other questions toward it, the way heavy objects bend the space around them. Because once you start wondering whether the past happened, you start wondering what a person even is without one. John Locke thought he had this figured out. Back in 1689, he wrote his essay concerning human understanding, and in it he made a claim that sounds almost too clean. Personal identity is founded entirely on continuity of consciousness, specifically on memory. You are the same person as the child who scraped a knee on a gravel driveway only if you can remember scraping it. That's it. That's the whole test. Not your body, not your name, not the fact that other people insist you're the same person, just the thread of remembered experience, stitched from one moment to the next. And for a while that feels reasonable. You remember yesterday. Yesterday you remembered the day before. There's a chain, and you're at the end of it, and the chain is you. But here's where it gets quiet and strange. A Boltzmann brain, this hypothetical mind that fluctuates into existence with a full set of fabricated memories, would pass Locke's test perfectly. It would remember a childhood. It would remember a first day of school, a conversation with a friend, the taste of something it ate last Tuesday. None of it happened, not a single moment of it, but by Locke's own standard, that doesn't matter. The identity is just as real, built from the same raw material of remembered experience, even though none of those experiences ever occurred. The Boltzmann brain has exactly the same claim to personhood as any evolved human being, which means either Locke's theory is more generous than he intended, or personhood is a much thinner thing than we like to believe. There's a kind of vertigo in that, not the dramatic kind, more like the slow realization that the floor you're standing on might not go down as far as you assumed. And it gets worse, or maybe not worse, maybe just more honest. About a century after Locke, a Scottish philosopher named Thomas Reid looked at this memory theory and found a crack in it. A serious one. He published it in 1785, and it's called the Brave Officer Paradox, and it goes like this. A boy is flogged at school. He grows up and becomes a young officer who still remembers that flogging. Later, the officer becomes a general. The general remembers being the young officer, remembers the battles, the commands, the weight of responsibility, but he's forgotten being the boy. He has no memory of the flogging at all. Now, by Locke's rule, the officer is the boy because the officer remembers being the boy. The general is the officer because the general remembers being the officer, but the general is not the boy because the general doesn't remember being the boy, and that's a contradiction. If A equals B and B equals C, then it has to equal C. That's just how identity works, or how it's supposed to work. Reid's point was that memory can't be the whole story. The chain breaks, links fall away. And if identity is just memory, then you're not even the same person you were 10 years ago, not in some poetic, metaphorical sense, but in the strict, logical sense that the connection has been severed. Now take that worry and hand it to the Boltzmann brain, and something even stranger happens. Because the Boltzmann brain doesn't just have a chain with missing links. It has no chain at all. Its memories don't connect to anything. They don't lead backward into a real past because there is no real past. The memory of being a child doesn't connect to an actual childhood. The memory of yesterday doesn't connect to an actual yesterday. The whole thing, the entire sense of being a person with a history, is a single, unconnected link, one bead with no string. Reid showed that even real memories, honest ones, can fail to hold identity together. The Boltzmann brain takes that failure and makes it total. If your memories were fabricated, all of them, every last one, then the thing you call you was never built up over time. It was assembled all at once, like a photograph of a bridge that was never actually constructed. And yet, you'd still feel like you. That's the part that's hard to sit with. There's another layer to this, and it comes from a physicist named Hans Reichenbach. In 1956, he published a book called The Direction of Time, and in it he drew a line between two things you might not expect to be connected, entropy and memory. Reichenbach showed that records, and he meant this broadly, footprints in sand, photographs, the neural traces that constitute what you experience as remembering, can only form in the direction of increasing entropy. A memory is not just a thought, it's a physical record created by an irreversible thermodynamic process. When you remember something, what's actually happening is that a past event left a mark on the physical world, a mark that could only be left because entropy was rising, because the universe was moving from order toward disorder. If entropy were decreasing, if the arrow of time were reversed, records of the past couldn't form at all. There would be nothing to remember, because remembering requires a particular direction of thermodynamic flow. So the very existence of your memories, the fact that you have them at all, is thermodynamic evidence. Evidence that entropy has been increasing. Evidence that you exist in a universe with a particular history, a particular arrow, a particular direction. But the Boltzmann brain denies exactly this. The Boltzmann brain is a momentary fluctuation, a brief, local decrease in entropy that produces the illusion of a mind with memories. It has memories, yes, but those memories aren't records of anything. They weren't created by irreversible processes unfolding over time. They were created all at once by a statistical accident, and they point to a past that never generated them. It's like finding a footprint on a beach where no one ever walked. The shape is perfect. Every ridge, every curve of the toe, but the foot that supposedly made it never existed. The sand just happened to settle that way. And so you're left with this strange, quiet tension. Your memories feel like proof that things happened, that you were there, that the past is real and heavy and yours. Reichenbach showed that in a normal universe they are exactly that thermodynamic proof written into the structure of the world. But if you're a Boltzmann brain, that proof is forged, perfectly forged, and you'd never know the difference. That's the thing about evidence that could be fabricated. It doesn't stop feeling like evidence. It still has the weight of it, the texture. You just can't be entirely sure what it's evidence of. And maybe that's the strangest part of all this. Not that your memories might be wrong, but that they feel so physically real. Because they are physical. Every memory you've ever formed, your first day of school, the sound of a door closing behind someone who wasn't coming back, the smell of rain on hot concrete, each one was burned into your brain through actual, measurable thermodynamic work. Neuroscience has mapped this pretty clearly now. When you form a long-term memory, your neurons strengthen the connections between them through a process called long-term potentiation. And that process costs energy, real physical energy. Your brain spends it to rearrange its own architecture to make certain pathways easier to travel than others, and in doing so it generates heat, a tiny amount, an amount you'd never notice, but it's there. Every memory you carry is a small, irreversible expenditure of energy, a place where order was imposed on the chaos of your neurons, and the price of that order was paid in entropy released into the universe. There's something almost sacred about that if you think about it long enough. Your memories aren't just patterns of electrical activity. They're thermodynamic events, little pockets of irreversibility. You can't unremember something the way you'd erase a whiteboard. The physics doesn't work that way. There's a principle in information theory, Landor's principle, that says erasing or overwriting a piece of information must release a minimum amount of heat. Must, not usually does or tends to. Must, it's a law, so when your brain overwrites an old memory with a new version of events, when the details shift and blur over time, that rewriting has a physical cost too. The universe notices. It gets a little warmer, a little more disordered. So your memories are real in at least this one undeniable sense. They happen to the universe. they left a mark, not just on you, but on the total balance of order and disorder in everything that exists. Each one nudged the cosmos a tiny bit further along its long slide toward maximum entropy. Which makes it all the more unsettling when you learn that this connection between memory and entropy might run much deeper than neurons and synapses. In 2000, a philosopher named David Albert wrote a book called Time and Chance, and in it he gave a name to something that physicists had been quietly assuming for over a century. He called it the past hypothesis. It's simple to state: the universe began in a state of extraordinarily low entropy, very ordered, very unlikely, and everything since then has been a slow unraveling. That might sound like just a fact about cosmology, a statement about the Big Bang, but Albert argued it was something more fundamental than that. He said the past hypothesis isn't just a description of how things happen to start, it's a precondition for knowledge itself. Without it, you can't trust anything, not fossils, not light from distant stars, not your own memories. Here's why: if the universe didn't start in a low-entropy state, then there's no reason to believe that the traces of the past we find around us, geological layers, carbon dating, the cosmic microwave background, the scar on your knee from when you were 7, actually came from the events they seem to point to. They could just as easily be random fluctuations, momentary dips in entropy that happen to look like evidence of a coherent past. The past hypothesis is what gives records their meaning. It's what makes a fossil instead of just an oddly shaped rock. Albert thought this assumption had an almost Kantian status, not just an empirical fact, but a necessary condition for the very possibility of knowledge about what came before. Without it, the whole project of learning from the past collapses, not because the past didn't happen, but because you'd have no way to distinguish a real past from a convincing fake one. And that's where this gets quietly devastating. Because if you take the Boltzmann brain hypothesis seriously, if you entertain the possibility that you might be a momentary fluctuation in an otherwise disordered universe, then the past hypothesis is exactly what you can't assume. A Boltzmann brain doesn't emerge from a low-entropy beginning. It emerges from noise, from randomness, from the vast, featureless equilibrium that the universe is heading toward, or might already be in. And in that case, your memories don't trace back to real events through an unbroken chain of increasing entropy. They're just part of the fluctuation, part of the blip. The physicist Sean Carroll thought about this problem for a long time. In 2017, he published a paper called Why Boltzmann Brains Are Bad. Not bad as in unlikely, bad as in logically self-defeating. He introduced a concept he called cognitive instability. The idea goes like this: if you believe in a cosmological model that predicts most observers in the universe are Boltzmann brains, random fluctuations with false memories and unreliable reasoning, then you have to accept that you are most likely one of those observers. And if you're a Boltzmann brain, then your reasoning is just a random fluctuation too. It has no correlation with reality, no connection to truth. Your belief in the model that led you to this conclusion is itself just noise. The theory eats itself. It's not that it's wrong exactly. It's that believing it undermines the very faculties you'd need to evaluate whether it's true. It's like trying to use a ruler to measure whether rulers are accurate. If the ruler is broken, you can't trust the measurement. And if most observers have broken rulers, broken minds, random thoughts, fabricated evidence, then the conclusion that most observers have broken rulers was probably reached by a broken ruler. Carroll thought any good cosmological theory should avoid this trap. If your model of the universe predicts that rational thought is cosmically rare and almost certainly not what you're doing right now, then something is wrong with the model. Not because the universe owes us rationality, but because a theory that destroys the basis for believing in theories isn't really a theory anymore. It's a kind of intellectual vertigo with no floor. And yet, and this is the part that keeps you up at night, or maybe, if you're lucky, the part that lets you finally drift off, you can't actually prove you're not in that vertigo right now. You can only notice that your thoughts feel coherent, that your memories seem to connect, that the evidence around you appears to tell a consistent story. and then you decide quietly without proof that this is probably enough. That feeling of probably enough, it's worth sitting with for a moment, because there's something almost biological about it, something wired into the architecture of the brain itself. There's a region called the orbitofrontal cortex. It sits just behind your eyes roughly, and one of its jobs is startlingly specific. Every time a thought surfaces, every time a memory floats up, this region runs a kind of check, not a slow, deliberate investigation. More like a bouncer at a door, glancing at a face and deciding in a fraction of a second, real or not real, actually happening or just noise. The whole process takes about 200 to 300 milliseconds. Less time than a blink. And most of the time, you never notice it working. That's the point. It's supposed to be invisible. The filter runs, the verdict comes back, and your experience just continues, seamless. You remember breakfast, and the memory feels like breakfast. You recall a conversation, and it arrives with the texture of something that happened, not something you invented. When the filter breaks, when the orbitofrontal cortex is damaged, things get strange in a very particular way. Old memories start showing up uninvited, pushing into the present as though they're happening right now. A person might suddenly remember a meeting that took place years ago and insist it's still going on, or they'll describe events they only imagined with the same certainty they describe the room they're sitting in. Confabulation, it's called, not lying. They genuinely can't tell the difference. The filter that separates what happened from what was merely thought, it's just gone. And that's what makes the Boltzmann brain scenario land differently once you know this. Because the thought experiment isn't just asking whether your memories are accurate. It's asking what happens when there's nothing behind the filter at all. No real breakfast, no actual conversation. Just the machinery of sorting, the feeling of recognition, the quiet hum of a mind convinced that everything it touches is solid and nothing underneath to justify the conviction. The filter still works. It still says real, but there's no reality for it to be right about. It's a strange kind of haunting when you think about it. Not a ghost in the machine, but a machine built entirely out of ghost. Halfway around the world, and about 12 centuries ago, a philosopher named Adi Shankara was circling something remarkably similar, though he arrived at it through meditation and scripture rather than thermodynamics. Shankara was working within the Hindu tradition, drawing heavily on a text called the Mandukya Upanishad, and his central argument was disarmingly simple. There is no meaningful difference between dreaming and waking, not metaphorically, not as a poetic gesture. He meant it as a description of how consciousness actually works. The dreaming mind, he pointed out, constructs an entire world, people, places, emotions, narratives, from absolutely nothing but itself, no external input. No sensory data, just raw awareness folding in on itself, building a universe out of its own activity. And you believe it completely. While you're inside the dream, it's real. The ground holds your weight, the faces are familiar, the story makes sense. It's only when you wake up that you realize none of it was there. Shankara called the force behind this illusion Maya, a kind of cosmic projection, the fundamental tendency of consciousness to generate the appearance of a world that doesn't ultimately exist. And he didn't stop at dreams. He argued that waking life operates on the same principle. The colors, the textures, the feeling of solidity under your feet, all of it Maya. The only difference between waking and dreaming in his system is that waking is a more stable dream, a more persistent one. But persistence, he would say, is not the same as truth. He proposed that there's a fourth state of consciousness beyond the three we know, beyond waking, dreaming, and deep sleep. He called it Turiya. And Turiya is strange because it isn't really a state at all, not in the way we usually mean. It's what's left when all the projections stop. When the dreaming mind stops building worlds and the waking mind stops insisting that its world is the real one. It's the awareness that was there the whole time, underneath all the construction, quietly watching the show. Whether or not you find that persuasive, and honestly, it's the kind of idea that you can turn over for years without settling, there's something about it that rhymes with the Boltzmann brain in an unsettling way. Both are asking, what if the experience of reality is all there is? What if the world is something the mind does, rather than something the mind is inside of? And then there's Buddhism, which walks up to the same cliff from yet another direction and says something even more disquieting. There was never anyone standing at the edge to begin with. The Buddhist doctrine of anatta non-self doesn't argue that the self is an illusion in the way Shankara might. It argues that the self is a process, a temporary assembly. The Buddhist tradition breaks a person down into 5 aggregates: form, sensation, perception, mental formations, and consciousness, and says, look carefully at each one. Which of these is you? Form changes, sensations arise and vanish, perceptions shift. Mental formations, your habits, your tendencies, your patterns of thought, they're in constant motion. And consciousness itself isn't a thing, it's a stream, a sequence of moments of awareness, each one lighting up and dying like a spark. There's no core, no kernel, no irreducible I sitting behind the eyes watching it all happen. There's just the happening. The aggregates come together, hold a shape for a while, long enough to feel like a person, long enough to accumulate memories and preferences and a name, and then they come apart, and nothing was lost because nothing permanent was ever there. A Boltzmann brain would be the most extreme version of this, an observer assembled from chaos, carrying a full sense of identity, a name, a history, a feeling of continuity, and none of it anchored to anything real. No past that actually happened, no body that actually grew, just the 5 aggregates, flickering into existence for a moment, performing the act of being a person, and then dissolving back into thermal noise. Anatta demonstrated not through meditation or philosophical argument, but through physics. The universe, accidentally proving the Buddhists right. There's something almost gentle about that if you let it be. Not the loneliness of it, that part is vast and cold, but the permission in it. If the self was never a fixed thing to begin with, then there's nothing to lose. The aggregates gather, the experience happens, and for however long it lasts, it's complete. Not because it's permanent, not because it's grounded in something solid, but because completeness was never about permanence in the first place. And maybe that's the right frame of mind for what comes next, because the idea that completeness doesn't require permanence is an old one, and it keeps showing up in the strangest places. Jorge Luis Borges wrote a short story in 1940 called The Circular Ruins. It's about a man, a quiet, deliberate man who travels to an ancient temple with a single purpose, to dream another human being into existence, and he does it. Organ by organ, thought by thought, he builds a person inside his own sleep. He dreams the lungs first, then the heart, then the network of veins. He dreams eyelids, he dreams the capacity for wonder. Night after night, year after year, until the dreamed man is whole and breathing, and can walk out into the world on his own. It's a beautiful, exhausting act of creation, and the story could have ended there, this strange miracle of will and imagination, but Borges doesn't let it end there. In the final lines, the dreamer walks through a fire and discovers that the flames don't burn him, and he understands, with relief, with humiliation, with terror, that he himself is being dreamed by someone else. That's the whole story, just that turn, and what's remarkable is how many emotions Borges packs into that single realization: relief, because now there's an explanation for the strangeness of his own existence. Humiliation, because everything he thought he'd built was built on nothing, and terror, because the recursion doesn't stop. If he's being dreamed, then the one dreaming him might also be dreamed. There's no floor. Borges couldn't have known about Boltzmann brains. He was writing about mythology and mirrors and labyrinths, but he seemed to intuit the recursive horror at the center of the hypothesis, the suspicion that the dreamer is always also the dreamed, that every act of observation might be observed by something that doesn't know it's being observed in turn. It's not a logical proof. It's a feeling, one of those feelings that starts in your stomach and doesn't really go away. And if Borges arrived at that feeling through poetry and philosophy, Philip K. Dick arrived at it through paranoia, which honestly might be the more honest route. Dick spent his entire career writing stories that read like dispatches from Boltzmann brain cosmology decades before most people had heard the term. In We Can Remember It For You Wholesale, published in 1966, a man discovers that his memories of a trip to Mars were implanted. They feel completely real. They have texture and emotion and continuity, but they were manufactured. And the truly unsettling part isn't the deception, it's that the implanted memories are indistinguishable from real ones, not just to an outside observer, to the man himself. There is no inner test he can perform, no way to reach into his own mind and feel the seam where the real stops and the fabricated begins. 3 years later, Dick published Ubik, which takes it even further. In that novel, the perceived world is a decaying simulation being maintained by a dying mind. Reality peels away in layers, products on shelves regress to older versions of themselves, technology slides backward, and the characters can never be certain which layer of experience is the base one, if there even is a base one. Dick was haunted by what he called the black iron prison, this persistent conviction that consensus reality, the world everyone agrees is real, was actually a constructed illusion. Not a metaphor for social control or media manipulation. He meant it literally. He believed, or at least he couldn't stop believing, that something fundamental about the shared world was fake, that the walls were painted on. And here's what's strange about Dick. He arrived at the same destination as Boltzmann, the suspicion that the experiencing self might be an accident, a fluctuation, a momentary arrangement of information with no ground truth beneath it, but he got there through completely different means. Boltzmann used thermodynamics and statistical mechanics. Zhuangzi, centuries before either of them, got there through a butterfly dream. Dick got there through paranoia and amphetamines. The roots couldn't be more different. But the place they arrive is the same dark room, and they're all standing in it, unable to find the light switch. There's something almost funny about that, the idea that the deepest question in cosmology, are we real, keeps getting independently rediscovered by people who have no business talking to each other. A 19th century physicist, an ancient Chinese philosopher, an Argentine librarian, and a science fiction writer in California who couldn't pay his rent. They all found the same crack in the floor. But here's where it takes a different turn, because physics might have found a way to seal that crack, or at least to argue that it doesn't matter. It has to do with the Higgs boson of all things. Current measurements suggest that the electroweak vacuum, the quantum field state that underlies everything we observe, might be what physicists call metastable. That's a wonderful word. It means stable, but not permanently. Stable the way a ball balanced on the rim of a bowl is stable. It'll stay there as long as nothing nudges it, but if something does, it falls. The idea is that the vacuum could eventually decay through quantum tunneling into a lower energy state. And if that happens, not in any one place, but spreading outward at the speed of light, it would fundamentally destroy the conditions needed for Boltzmann brains to form. The de Sitter space, that vast, endlessly expanding equilibrium where thermal fluctuations have eternity to produce impossible things, would simply stop being that kind of space. The party would be over before the strangest guests could arrive. There's something quietly poetic about that. The universe's own instability might be what saves us from the conclusion that we're accidents of its equilibrium. The fact that the ground isn't solid, that the vacuum itself might someday give way, is precisely what makes it plausible that we're real. That we're not Boltzmann brains hallucinating a history, but actual products of an actual past, living in a universe that hasn't had time to go fully insane yet. It's a strange kind of reassurance, not the universe is stable and you're safe, but the universe is fragile, and that fragility is why your memories are probably genuine. The floor might collapse someday, but the fact that it hasn't yet, the fact that it could, means the floor is real while you're standing on it. And maybe that's enough, maybe that's the only kind of enough there is. So in January of 2026, 3 researchers, David Walpert from the Santa Fe Institute, Carlo Rovelli, and Jordan Scharnhorst, published a paper in the journal Entropy, and what they found was, in some ways, the quietest bombshell in the history of this entire debate. They showed that the Boltzmann brain problem and the so-called past hypothesis, the idea that the universe started in a low entropy state, and that's why time flows forward, are mathematically the same thing. Not similar, not related, identical. They're both just different ways of choosing which slice of present-day data you trust and which you explain away. That might sound technical, but the implication is enormous, and also strangely freeing. Think about it this way. The past hypothesis says, trust your memories. The universe began in an ordered state. Entropy has been climbing ever since, and your recollections are genuine recordings of things that actually happened. The Boltzmann brain hypothesis says, don't trust your memories. You might be a momentary fluctuation in a sea of chaos, and everything you remember, your childhood, your breakfast this morning, the fact that you're listening to this, might be a false imprint in a brain that didn't exist 5 minutes ago. Those sound like opposite claims, but the 2026 paper demonstrated formally that neither one is more physically justified than the other. They're mirror images. Each one starts by fixing a different subset of what we observe right now and then runs the math in a different direction. Physics doesn't pick a winner, it can't. And here's the part that's been hiding in plain sight for over a century. A lot of the arguments people have made, smart people, careful people, about why the Boltzmann brain scenario is absurd or why the past hypothesis must be correct. Those arguments are circular. They've been circular this whole time. Nobody noticed, or maybe people noticed and didn't quite know what to do about it. The circularity works like this. To argue that your memories are real, you need entropy to have been increasing. That's the condition under which memories function as genuine records of the past. A footprint in the sand means someone walked there, but only if the sand was smooth before the foot arrived. If entropy was decreasing before this moment, then your memories aren't records, they're accidents. Patterns that look meaningful but weren't caused by the events they seem to depict. So you need increasing entropy to trust memory, but you need to trust memory to establish that entropy has been increasing. The evidence for the past hypothesis is your memory of the past, and the reliability of your memory depends on the past hypothesis being true. It's a loop, a gentle, invisible loop that physicists have been walking around in for a very long time. That's a strange thing to sit with, not frightening exactly, just quiet, like discovering that the foundation of a building you've lived in your whole life isn't anchored to bedrock, it's floating. It's been floating the whole time, and somehow the building still stands. What the paper proposed instead is something called the entropy conjecture framework. It models entropy as a process that's symmetric in time. It doesn't care whether you're looking forward or backward, and it doesn't privilege any particular moment. Under this framework, the choice between trusting your memories and doubting them isn't a conclusion you arrive at through physics. It's a boundary condition, an assumption you bring to the table before the equations start running. Like choosing which end of the telescope to look through. And that means the debate, this century-old cosmology scale argument about whether you're real, doesn't belong to physics at all. It belongs to philosophy, which, if you think about it, is where questions about memory and identity and trust have always lived. Physics wandered into the room, knocked some things over, and the 2026 paper is gently suggesting that maybe it should wander back out. There's something almost tender about that. The universe isn't going to tell you whether your memories are real. It doesn't have an opinion. The math works either way. You're left with a choice, not a proof, but a choice about whether to trust the shape of your own past. And maybe that's what it always was. Maybe the floor you're standing on was never going to come with a certificate of authenticity. Maybe the fact that it holds your weight is all the reality it needs. Maybe the fact that your memories feel like yours, that they carry warmth and specificity, and the odd sharp edge of something you wish you could forget, maybe that's not evidence in the scientific sense. Maybe it's something older than evidence. The floor is real while you're standing on it. Your memories are yours while you're holding them. And the universe, vast, indifferent, possibly just a long exhalation of entropy finding its way downhill. The universe doesn't mind either way. It has no stake in whether you trust it. So you might as well. You might as well trust the weight of your own head on the pillow. Trust the softness of the dark. Trust that the things you remember happened to someone and that someone was you, and that's enough. Not because the math says so, because you're here. Because the question itself, are my memories real, could only be asked by someone who remembers enough to wonder. And that's a kind of answer, isn't it? Not a proof. Just a quiet, circular, strangely comforting kind of answer. The kind that lets you close your eyes. So maybe that's where we leave it tonight. Not with an answer, because this one doesn't come with answers, but with something quieter than that. The floor is real while you're standing on it. Your memories are yours while you're holding them. And the question of whether any of it is anchored to something deeper than your own experience, well, that question has been asked by physicists and philosophers and dreamers for centuries now, and none of them lost sleep over not solving it. Or maybe they did. Either way, the dark is soft, the pillow is real enough, and you were here for this. That's a kind of proof all on its own. Rest well.